My name is Gabriel West. I'm a senior mechanical engineering major with my mentors, Dr. Sushil Doranga and Dr. Jenny Zhou. I have done research over the vibration response prediction of printed circuit boards used in the transportation industry. So, the significance behind my research is that in most of industry, they will go and simulate a PCB or printed circuit board as part of an electronic package in an isotropic manner. What this means is that the PCB would respond to different forces equally no matter what direction, because the mechanical properties are the same in the X, Y, and Z axes. But in actuality, as you'll see later on in the next slide, that isn't always the case due to the construction of the PCB. And my hypothesis is, because of this change in setup, I believe that the response of the simulations response of a simulation with an isotropic compared to an orthotropic will be varied enough that it would not be accurate to simulate your PCB as an isotropic PCB compared to an orthotropic PCB. And we will be proving this hypothesis by a mixture of simulations and physical testing, with the importance of eventually having these values, once we find the physical values, to convert them to actual mechanical properties for future research. Now, for the PCB materials as a whole, you can see that the image on the right shows how it's not a homogeneous mixture in just one solid thing, but it's actually layered in different materials. And that layering effect is the reason why the orthotropic material comes into play and varies due to the way that the forces, once applied to the PCB, spread out throughout the PCB. If you look on the image on the right, you can see the 4 different models that we used from existing literature to actually be used for our simulations. The isotropic, which is model 1, is our control to kind of show what most of industry and some existing literature actually does, while the other 3, models 2, 3, and 4, are orthotropic models that will be used to not only compare orthotropic to isotropic, but also compare the simulation results of these 3 to our physical experiment once we go through and get that actual data compiled. So the experimental setup, how we have it set up, is you start off with the function generator, which is the image on the far left, that creates, in our scenario, a certain sine wave at a certain frequency. And that signal then gets sent out to 2 different places. It gets sent to the oscilloscope, where we can read the actual frequency. Due to the function generator being an analog system, we wanted to have a way of getting an exact measurement of the frequency, and we did that through the oscilloscope. But it also goes out to the amplifier, which makes it to where you can have a set amplitude and a set force being applied for the frequency itself. And that frequency then gets sent down to the shaker, which is the blue image, or the blue and black mechanical device. And that actually turns that signal into a mechanical vibration. And this vibration then allows to actually send that vibration signal to the PCB itself. And the data from that application is being collected by the impulse sensor, which is the big gray block on the top of the shaker, or this bottom image right here. And that records the reference forces that are being applied to the PCB itself, while the accelerometer, which is the image right above it, actually measures the dynamic response in G's of acceleration. And that raw data is then transferred to the data acquisition box, which is this black box right here. And then that then converts the data to a visual, for something that can be visually represented on our DAQ software from our computer on the far right. So here's an extra page that kind of goes into a little bit more detail about how each thing is set up and what they're used for. I just went over that in the previous slide, so I'm going to just touch on a few things real quick. The first is that the accelerometer needs to be placed in the same position throughout all simulations and experimentations. And in our scenario, it is 17.5 centimeters from the left edge and 5.5 centimeters from the bottom edge. And this is to ensure that all the response data throughout the testing and simulation matches and can actually work with one another due to them being from the same location. And the last thing on this slide I want to mention is how our DAQ program actually runs both transient and steady state simulation. And the transient data actually comes in when you're first applying the force. It's where that PCB is getting up to that natural frequency. And due to that not being a constant, we went ahead and truncated that from our testing itself. And then we took the peak value of the steady state response. So what that means is that's the highest point of force that's being applied and the highest response that's being received from the PCB, but it's a repeatable constant through the wave itself. So that is that's the highest constant value we can possibly get for the simulation, to where we wanted to make sure we have that peak performance of the PCB itself. Now, for the simulation setup itself, there's a couple different things we wanted to go into. The first is that we used 3 different elements. We used shell, quadrilateral, and tetrahedral, as well as changing the size of all 3 of those elements to see if the results change based on one or more of those scenarios. Fortunately for us, they all yielded the same results, so we didn't have to worry about which element was used. Because of that, we went ahead and just used the kind of industry standard, which is the tetrahedral elements for the meshing, and that's due to allowing us to actually get the holes for the bolts to go in on the PCB. We used those to actually we used the tetrahedral so we could allow that rounded shape, which you can't do in the quadrilateral, and then it's also a solid element, so that's why we didn't use the shell. Now, these results that I'm talking about, they actually come into play in the form of natural frequencies, mode shapes, and responses at the given frequencies that we test. And we'll go into more detail on that. Now, after simulations, this is the data we ended up receiving. The top portion is the entire test from 0 to 600 hertz. But as you can see, the very first natural frequency, which is that first big peak, by far yielded the strongest results. So we went ahead and zoomed in on that and used that as our primary testing point, and that's what we looked at because that's where we were going to get the most response out of. And right here you can already see that the orange model 1 is our isotropic model, and you can see that there's already a variation between the isotropic and orthotropic models, which is kind of starting to lean the direction of being able to simulate the orthotropic as a necessity, because the isotropic just would not give the same response. Now, here's a quick example of our first test, which was our hammer test. The video on the left you can see is Dr. Doranga and myself doing the testing for the hammer test. He is applying the forces and actually creating the raw data, and then I am looking at the computer and registering the data to see if there's any values that didn't work right, or Dr. Doranga double hit the PCB so that would create nonlinear responses and make them non-valid. So here's the results for our first test. Unfortunately, this is just the clamped results due to the clamped free having issues with sensitivity for the hammer, and then also getting some feedback and noise in the testing itself from the testing apparatus setup. But luckily for the clamped test results, they were super clean, and we had some extremely constant values, which you can find in the purple tables. What these frequencies set up to be were 58 to 59 hertz, 81 to 82 hertz, 126 to 127 hertz, and 136 to 137 hertz. These were the groups of frequencies that constantly repeated themselves. So those were the tests that we ended up focusing in on when we were sweeping from 45 to 330 hertz for our physical testing for the modal shaker. And here's a quick example of what the modal shaker testing looked like. These are both configurations and also what the raw data looks like when you're actually doing the testing itself on our DAQ software. So here's the physical experimentation data and our final data for our research so far. As I stated earlier, the constant load applied for each simulation and each test was 1/2 pound. And you can see right away that Model 3, which is the bluish, purplish line, is by far the most consistent compared to the physical experimentation. So those are the two that we would end up taking to further the research, which I'll go over in a couple of slides. But you can also see here that the isotropic and orthotropic models are very different and they do not really align with one another. So this gives credence to our conclusion where you do indeed need to simulate a PCB as an orthotropic material because the response just simply will not be the same. Because like if you look at it, we had a response of 55.13 hertz for the first natural frequency for the experimental data compared to 78.6 hertz for the isotropic for the clamped, and the clamped free still has a gap of 6 hertz for the natural frequency, which is just too large to be able to simulate. While the isotropic or the Model 3 values very, very closely relate to the experimental data. Now, some difficulties that were encountered is, first of all, designing the apparatus. The dimension limits that we had with the 3D printer that we were using definitely had some, it made me have to redesign and rebuild a couple of times just because things wouldn't quite line up or they wouldn't fit in the 3D test bed. So we had to go through and size it down to make everything work properly. Also, we had issues with the printing failing. Like we had 2 pieces that had to be completely scrapped because the extrusion started to warp during printing, and you'll see images of those later on in the test, or in the presentation. But one issue that we really came into and realized that was going to be a problem when we were doing our simulations and our experimentation was using PLA, which we had to use for the design limit or the cost limit that we had. We didn't have the money to purchase billet aluminum which we wanted to do, but that's due to the modulus of elasticity of PLA ranging anywhere from 0.5 to 3 gigapascals, and we had no way of truly knowing what exactly the extrusion we used, what its exact value was. So we had to do some guesswork and just kind of throwing in values and seeing how it reacted. But also, because it's so low, we would hit some of those natural frequencies of the PLA during our testing, and it would excite the PLA, which would throw feedback noise into our test results, which would give us nonlinear responses, and we couldn't use that data, which is the big issue that we came into when we were doing the hammer testing for the clamped free configuration. Now, so what our future works will be. Like I said earlier, we will take the physical experimentation data and Model 3 simulation data and compare those two to find a benchmark for the mechanical properties of our physical PCB in order to move on to our future projects. And what that future project will be is taking a printed circuit board assembly, which is a printed circuit board with all of the chips and sensors and stuff like that on it. And we will do the same testing that we did with the PCB with the PCBA. And then we will try and compare the two and see the differences in the response rates and values and stuff like that. And the reason why we're doing this is to basically do another step of the research we did during the summer, which is to see if just simulating a PCB with the proper mechanical properties is valid enough to use for, once again, the simplicity and speed of the simulation, or if it's warranted to simulate the entire PCBA due to the change in responses and stuff like that of the PCB when related to the PCBA. And we'll be going through that process, as in the isotropic and orthotropic argument, most of industry also will just simulate a PCB compared to an entire PCBA. So that concludes my presentation. I will leave you off with a couple of extra photos showing some of the issues we came into play with the warping printed pieces, and then also a picture of my entire project all together and kind of see how it's all set up. So thank you. Have a great day.